Okay, so our next speaker is Peter from IBM New York. So we have the pleasure, he came all the way from the US to see us. Peter did his PhD with Rainer Blatt, and he also did a postdoc with him. And he also worked at IBM before, and now he's been working at IBM for 4 years, right?
4 years.
So he'll tell us about quantum benchmarking, and okay, there's one important thing. You all open Instagram and you follow his dog at 6-toe Mo, and it's a dog with 6 toes. Is that correct?
Yes, he has 6 toes, so that's why it's called 6-toe Mo.
And yeah, he's trying to make him famous, so let's all make his dog famous.
All right, can you hear me? Great. Well, let's talk about quantum benchmarking. I made this talk on purpose a little bit overloaded in the sense we're probably not going to go through every single slide, but quantum benchmarking is sort of like a whole zoo, and I felt like it's more important that you have like maybe one thing where you can look up these things with a lot of references, and the references are in the slide, so whenever you get access to them, you can just look it up yourself. Yeah, it's basically divided in 4 parts. A quick introduction on what quantum benchmarking is, and then like the 3 levels that I believe are the most important ones, or the way I think of it in terms of like dividing it, device, system, and holistic benchmarks. So, well, why do we even do benchmarking? And I made this slide on purpose really chaotic because quantum benchmarking is a little bit chaotic. There's just so many things. There's so many techniques, so many questions, and so many answers. But you know, some of them are like, how do we even characterize this black box? When you're an experimentalist and you get a new device, often a priori you do not know what are the frequencies, what are the couplings, what is this, what is that. Then you know, we want to answer questions. How well does a quantum operation work? Do we even know that we do the right quantum operation? Is an X-pi gate really an X-pi gate? Next question is, how do we define probe? You know, you want to improve stuff, but how do you know you improved? And you know, last but not least, we want to know, does a quantum computer do anything useful? And maybe we want to compare different architectures, devices, and so forth. So let's start with a couple of definitions. To me, benchmarking is just like a experiment, algorithm, procedure that you use to sort of like characterize, verify, and validate a quantum device, and this is known as QCVV. Sort of in the best case, benchmarking should be scalable in terms of like you could expand it to more and more qubits. It should be device independent, which is not always true. And very often, but not all the time, benchmarking just indicates that something went wrong, but it's not often so easy to extract what really went wrong. Metrics is sort of what we're aiming for. Like, this could be a error, a fidelity, heavy output probability, cross entropy, whatever you want to define, and often sets a threshold where we want to go beyond or below, you know, this magic 4 nines for fault tolerance or whatever. A few more definitions. QCV, you know, these definitions are not written in stone. They're like, you know, depending on how you interpret it. Characterization is basically you just want to measure and like define the parameters of your system. Like you have a device, you want to know its frequencies, its couplings, and so forth. Verification, on the other hand, is like, you know, you've implemented a quantum operation, and now you want to know how well you did that. Not only knowing if it's the right one, but also like how good it is. And validation is sort of more this broader term of like, well, does a quantum computer actually do something useful? You know, this is maybe not where we are at right now, but more important in the future. And so as an experimentalist, the way we think about it is this, what we call this internally, the Smolin spiral from John Smolin. Basically, you have your quantum system. You have a set of errors that you are aware of, you prioritize them, you try to fix them, and then with a orthogonal set of experiments, you try to verify that you made improvements. Then you find another set of errors, and you know, you just go down the spiral till you reach fault tolerance. This is not very much like reality because like, you know, it's not that sequential. Things go like back and forth. We have to maybe change things, gain new knowledge and stuff like that. But benchmarking is nothing new. That's not something we as a community have invented. We've been doing benchmarking for ages. This is the LinPack benchmark on some of the world's supercomputer, and I believe this slide is a little bit outdated because Summit is already not on the first place anymore. And we started doing that sort of with quantum computers. So this is just like an extract from Wikipedia, well, mostly between Honeywell and IBM on this benchmark that we call quantum volume that I will talk about later. All right. Let's start with the benchmark pyramid. This is what I kind of like to think about benchmarking in terms of a pyramid, where at the bottom of the pyramid, like the fundamentals, is device parameters, device benchmarks that define coherence times T1, T2, frequencies, couplings, crosstalk. Some systems have heating, some don't. Sometimes you have systems that lose an ion, or a qubit, I should say, or an atom, or whatever, a photon. And these benchmarks are often very specific to the qubit architecture, so they're not often easily transferable from one system to the other one. They're very dependent on device fabrication, device design. They can change drastically from one generation to the other of devices. Somewhere sort of like in between, I probably also call like readout, reset in this like device level benchmarking. If you go one level higher, we have subsystem benchmarkings, and these basically also include also like our control fields. Now, below here, you need something to probe your system, but often these controls do not have to be like perfectly calibrated. Now here, you want to really do gates. You have a control, you need to calibrate it, and so some of the benchmarks we use there are like all the variations of randomized benchmarking, and then all the variations of tomography from quantum process tomography, gate set tomography. I won't talk about Hamiltonian tomography. And somewhere in between here, it's sort of like this gate quantum state tomography, because you don't really probe like a quantum operation, but like you probe a state and sort of try to find out what's going on in your system. Yeah, and the A matrix is basically a way to quantify readout and reset errors. On top of that, we have the so-called holistic benchmarks. For instance, quantum volume, cross-entropy, multi-qubit, randomized benchmarking, and actually some of the applications. And to me, the sort of top tries to include every single bit of your computer stack, quantum computer stack, from software compilation to how these different bits and parts interact with each other. Maybe you have an additional set of control pulses for dynamical decoupling and so forth. So as we go from bottom to top, we sort of like have an increasing inclusion of all these bits and parts, but also the complexity increases, meaning often here on top, you just know something went wrong, but you have no chance to really figure out what it is. And in that sense, like the whole pyramid is actually important to know to characterize your entire system. All right, let's start with a very quick intermezzo, and we might just like fly through because I wasn't very sure on like where you guys are at. We all know we can write a pure quantum state in the vector form, and if you measure it in a computational basis, this is now perfectly without shot noise. You get like a 50-50 for superposition state. Oh, this is wrong. There should obviously be a plus here. We can generalize it a little bit more in the density operator or density matrix form, just by taking the outer product of our quantum state. Here on the diagonal, we have like the coefficients or the amplitude squares, basically the probabilities, and just like a few examples, you can write the Bell state in the vector form, or you can write the same Bell state in the density matrix form. When you measure it, again, with 50% probability, you get a 0-0 state or the 1-1 state in a perfect world. Now, the reason why we care a little bit more about density matrices in like an experiment is because they're a generalized way to describe quantum states, especially because we can now describe mixed states. A pure state is just an idealization of the real world. As an experimentalist, you will never encounter a pure state. Everything has a little bit of noise. And a mixed state is nothing else than just like a probabilistic sum or probabilistically weighted sum of pure states. As an example, let's take this pure state of being in the plus state. Again, the density matrix for it. Or, as an experimentalist, when you try to prepare that state, you sometimes over-rotate it specific to a qubit architecture. A benchmark or characterization techniques that you use for ions might not work for transmon qubits. So you need to know like your physical system, you need to know the physics of it, like the Hamiltonian. And one problem with them is they're not very strong in predicting like the performance of a quantum computer. They just like tell you what the device is, but they don't really tell you when you go once beyond that. And so I just want to go through a bunch of them is like measuring frequency T1, T2, and readout reset errors. Let's start with frequency spectroscopy. This is just basically the most basic thing that you can do. You have a system, you have a drive, you hit it with a drive, and you see the response. That's basically it. In a more like serious way is you apply a drive field to your idealized 2-qubit system or 2-level system that we call a qubit. You sweep, for instance, the frequency, and you see like a response. The nice thing about this is, well, you don't have to calibrate a lot of things. You just like shine in your laser fields, your microwave fields, B fields, whatever your drive is in your qubit architecture, and you record the result. And this is, for instance, a spectroscopy of 19 ions back in the days when I took that with like the motional modes. Now, once you have sort of found the frequencies, you can roughly calibrate like a pi pulse. It doesn't need to be perfect. And then you can do like T1 experiments. The only thing you do there is like you excite your qubit, you wait for a certain time, your qubit will decay, you wait for a little bit longer, your qubit will decay even more, and so you record like the decay curve, you fit that to an exponential, ta-da, that's your T1. Fairly simple. Now T1 is one of these errors where you start out in a product state, in a pure state, purity drops down because like, the Bloch sphere starts to shrink, so the Bloch vector becomes smaller and smaller. But eventually, you end up in the ground state, and the ground state is pure again. So this is called a non-unital error, because, or unital operations are operations that leave the maximally mixed state maximally mixed. Another technique to do spectroscopy is Ramsey spectroscopy. This requires a little bit more of calibration. You need to have a somewhat good pi over 2 pulse. So basically, you prepare your system in the superposition state, you wait, and you undo it. Now, if there's a difference between your drive field and the qubit frequency, you will accumulate a little bit of phase here that is proportional to the frequency difference and the time. And so as you scan the time here, you will see an oscillatory behavior. Knowing the time, you can immediately back out the frequency difference between your qubit and your drive field. This, for instance, can be used to measure dephasing. So the simplest way is, again, just through this Ramsey experiment, you get this sort of like oscillation that can be due to some like DC offsets. Like, as I said, your frequencies aren't perfectly calibrated, but on top of that, you get a little bit of a decay, which is due to phase jitters. With every experimental run, your phase just like changes slightly, or your frequency changes slightly, so as you average over it, it will decay with an exponential. You can undo some of these like low frequency noise components or DC noise components with a simple echo. So basically, if you have a constant rotation, if you do a pi echo, you undo it. And this is sort of what we often call a Ramsey echo or a Hahn echo. And then you get like a nice just exponential decay. The only reason why this starts at 1, this at 0 is just like depending on the definition of the second pulse. Either you undo it or you sort of like rotate in the other way. It doesn't really matter. All right. Let's move on to readout fidelities and resets. What we can do is prepare the system in 0, measure it, 1,000 times, and we know the label, this should be 0, and record it. We prepare the system in 1, we measure it again 1,000 times, we have the label, and label it. So here, blue are the experiments that I prepared in 0, red are the experiments that I prepared in 1, and sort of the X's in blue and red are the ones that are mislabeled, or sort of like errors. So for instance here, some of the 1 states just ended up in the 0 kind of cloud. This can be due to T1 or whatever. Sometimes these two clouds are just too close to each other, and then you can't really have a nice discriminator line. Now here, this is just like a simple linear discriminator. People have thought about many, many ways how to do like high-dimensional discrimination with like k-means or even like machine learning. Might help, might not help. But what we can do now is the so-called measure the so-called A matrix. And it's just like a matrix of these probabilities that you observe a certain bit given the true bit value. Meaning, if I prepare the system in 0, what's the probability that I really measure 0? If I prepare the system in 0, what's the probability that I measure the system in 1? And the diagonal of this A matrix gives us basically the readout sort of like error. Now, there are a few assumptions there that need to be sort of met. First of all, your state preparation error needs to be much, much lower than your readout error. If your state preparation is bad, well, you know, this is going to be just fully convoluted, right? Because you're never sure did you really start in the 0. Because like now, if you start 50 times of your experiment, 50% of the time in down and up, well, you can't tell anything. But I'd say if your reset is bad anyway, you shouldn't do quantum computation. Like you should spend more time in the lab. Another thing is if these two clouds, so this is just like a projection, a 1D projection of like the initial cloud on, for instance, a orthogonal line to this like discriminator line, for instance. If the two blobs are fairly separate and you can see two distinct distributions, you can attribute one of these to be like the reset error. And you see this is like orders of magnitude smaller here. And so we can also like identify reset errors even though they're like sort of somewhat convoluted. All right. Now you might ask the questions, okay, these are some of the things that work for most of the systems, I'd say. But what about things that are very specific to different qubit architectures? Well, they often boil down to spectroscopy in some form or another. For instance, this is basically the same experiment on two very different architectures answering two very, very different questions. In ions, we have like an address beam, and what we want to know is like how much of the light field spills out into the neighboring qubit. Here, in transmon qubits, we have this ZZ component that is like constantly entangling, and what it means is what is the control qubit frequency, or qubit frequency of the qubit that we're interested in, depends on the state of the spectator, right? We take exactly the same experiments here. Here, we do a Ramsey experiment to measure the AC Stark shift of the light leakage. Here, we do two Ramsey experiments to measure the frequency difference depending on if the spectator is in 0 or the spectator is in 1. All I want to say here is like, even though things might look very, very different on the physics level, these sort of like spectroscopies are sort of a very, very common tool for experimentalists. Some of the limitations about device benchmarking, well, what we have ignored so far completely, or more or less, is sort of the real interaction between like control signal and the qubit. Not quite true for the Ramsey, obviously, because there we measure sort of the difference often between the control and the qubit, but we can undo that with an echo, so we can get rid of that if need be. And the control itself can actually add a lot of more noise. This is like when I worked back then with ions and I moved over to transmon qubits, that was like the big difference is ions are perfect, your dry fields are crap, or like not as good. Superconducting qubits, microwaves are good, but your qubits are the problem, right? One thing that is completely ignored here, again, like calibration errors, and the dry Hamiltonian can add up way more complexity in your system. Oh yeah, and yeah, one thing that we often don't look at is like multi-qubit interaction. When you drive one, what will happen to the neighboring qubits and so forth. All right, any questions so far? What's the time? All right. Let's start with a second intermezzo about quantum operations. So if you have a closed system, you can describe any quantum operation just with a unitary transformation. If you think about a single qubit, it's just like rotation of the single qubit Bloch sphere around some predefined axis. Well, in reality, we do not have closed systems. Well, maybe the universe is a closed system, but like your lab system is not a closed system because it interacts with the environment. So the generalization of this process are quantum operations, and quantum operations can be described by so-called CP-TP maps. This is just a map that maps a density matrix in some Hilbert space into a different density matrix, and most often into the same Hilbert space. In literature, you often find two notations like epsilon or lambda, like Mike and Ike uses epsilon. A lot of like other literature uses lambda. I will stick with lambda for here. But you know, there's a good entry in the 8th chapter in Mike and Ike. There are sort of like two requirements to make this map physical. It needs to be completely positive. This is the CP part. And intuitively, what that means is we can't have negative. We can't have negative probabilities. Like probabilities need to be positive. And the second part, TP, is trace preserving, which basically means the probabilities have to add up to 1. Now, in this lecture, will stick to TP, but TP can be a little bit relaxed in case you have like measurements and you want to describe those, or if you have leakage out of your like computational subspace, because you know qubits are never or very rarely a perfect two-level system. Like transmons are these anharmonic oscillators, and you know we sometimes have leakage out of the computational subspace. Some of the common representations of CP-TP maps is the operator sum representation with Krauss operators, where basically we can use these A operators to describe the process. The nice thing about Krauss operators is you don't need to care about the real interaction between your system and the environment, because we just trace out the environment and we just look what happens to our system. This makes it like mathematically very convenient, but these are operators. We cannot measure operators. What we measure are some numbers, observables or like eigenvalues. So there's a transformation in a orthogonal basis, most often the Pauli basis that one can do, and basically transform these operators. And the transformation is encoded into this chi matrix, and basically this chi matrix is something that we can measure or try to infer, and it describes the whole CP-TP map. Another way to describe these maps is the Pauli transfer matrix. This is just a different representation, written in a slightly different way. I think people have sometimes preferences for one or the other. Seth Merkel prefers very much a Pauli transfer matrix. Luke Govaya, he prefers very much the chi matrix. Maybe some people from back in the days prefer chi because that's the way Ike did it with NMR, and it's written in the book. The nice thing about Pauli transfer matrices, though, is if you have two maps of two quantum operations, you can do matrix multiplication. This is something you can't do with chi. So this is kind of the nice thing about Pauli matrix. And the last thing is Choi. To me personally, Choi is only just like a way to reuse a lot of like the code bases that we have like from quantum state tomography that I will talk about, to just like reuse it to reconstruct a higher dimensional density matrix like MLE or whatever. This is a quick overview slide on these like different error channels, amplitude damping, dephasing, depolarization, just written in the three different representations. One thing that I also sort of like about the Pauli transfer matrices, the column, if it's trace preserving, the column is 1 and everything is 0. And if the first row is 1 and everything is 0, it's unital. And so you see here, amplitude damping is non-unital. That's sort of a nice quirk. All right, quick summary. So the generalization of state vectors are density matrices. The generalization of unitaries, which are a special case of CPTP maps, are CPTP maps. And I'm just going to mention it here, but not really talk about it. The generalization of von Neumann measurements are POVMs. And what we try to infer from benchmarking, mostly on the system level side, are sort of these parts here. So let's start with some of these system benchmarks. Right. To me, as I already mentioned, system benchmarks, they include your device, but not all the time. Or they always include your device, but not all the time, like control and calibration. Especially like this quantum state tomography, this is a little bit a weird one because, as you'll see, you have to prepare the state, so it depends on your preparation gates, but you don't really probe the gates. You probe a state. There are, I think, two distinct approaches. One is to sort of learn an average error of your quantum operation, and this is often done through some randomization, like RB and other means. Or you try to learn every single bit what's there of your quantum operation, but it just like scales really badly. So let's start with tomography. The basic idea is treat your system, whatever it is, as a black box. Poke it from all the sides. Try to infer every piece of information that you can get. You get sort of like a full description of your system, but it costs you exponentially in terms of like measurements, experimental overhead, even classical overhead. Some of the most common sort of methods are quantum state tomography, quantum measurement tomography that I'm not going to talk about, quantum process tomography, and gate set tomography, which is basically sort of like combine all these three previous things together and do sort of like a self-consistent estimate of all these like processes at once. Let's start with quantum state tomography. This is an experimental technique to infer an experimentally generated quantum state that you have no a priori knowledge. It's just like you don't know what it is. In a single qubit case, for instance, as an example, we can simply write it down in the different with the different polys, and like intuitively, what it all means is like you have your single qubit Bloch sphere, and your state points somewhere, right? And all you do is you describe it in your Cartesian coordinates, which are now your three polys, sort of, and that's vector physics or vector calculus. Nothing too exciting. And this is basically how we also try to measure it. So you prepare your state with some preparation operation, and then you try to measure the projection on all these three axes. And from that, you can like really point, like infer where your single cube Bloch vector points to. The sort of like thing that is not so nice about it is, well, it scales with 3 to the n. So for a single qubit, you need 3 measurements. For 2 qubits, you need 9 measurements, 27, 81, and so forth. So it grows very fast. The nice thing, on the other hand, is you know everything about the state that is to know, right? You can calculate some entanglement metrics, whatever that might be, log negativities. You can calculate purities, and so forth. One way to reconstruct it is just like linearly, as you measure these 3 parts of it, and you just build up your density matrix from whatever you measured. Now, you could have perfect readouts and perfect preparation pulses, but it's still quantum, and so we have to measure over and over again. And what you will have is so-called shot noise. You will have a distribution of your measurements. You won't get like a delta peak. So what can happen is now, if you try to reconstruct a state, you might end up in some with MLE. And one way around it is sort of like this Bayesian inference, which sort of like tries to find an honest solution to that. But you know, if you really want to know the details, personally myself, I've never used Bayesian estimation, but there are a couple of like review papers out there that you can look up yourself. Now, since this grows exponentially, quantum state tomography, there are a bunch of sort of tries to improve it. For instance, with compressed sensing, if you know that your density matrix is like sparse, you maybe don't need to measure every single entry of your density matrix, so to say. Matrix product state reconstruction or tomography is basically, you know, if you know that your correlation length in your system is bounded, meaning that your particle here or qubit here is not entangled with your qubit there, but only like over 3 sites, well, what you can do is just like 3 qubit state tomographies overlapping. And so instead of having like 3 to the power 10, you have 3 to the power 3 times m. So it really saves you a lot of time. But once your correlation length increases, you have to increase your subsystem size. And eventually, if your correlation length is across the whole system, well, then you end up with state tomography again. There are more newer ways on, this is not per se a tomography, but this is a way to try to infer certain nonlinear functions of your density operator. For instance, purity, Rayleigh entropy, von Neumann entropy, whatever you like. These days, even Fisher information. And something that is rather new, and personally I'm not too familiar with, is Scott Aaronson's and John Praskill's shadow tomography, which is kind of like what the closest classical description to your quantum state. But if you want to know more, these are the references. All right. Yeah, I think we don't have to really go through the summary in detail, but something that I didn't point out, and this is kind of one bad thing about state tomography, is it's very sensitive to spam. Meaning you can have the perfect state prepared, but if your measurement is wrong, you will infer the wrong state again, right? So this is something that you just need to keep in mind. Now, this has been brought up yesterday, that sometimes, and myself, have used quantum state tomography to infer the fidelity of a gate, right? You prepare a Bell state or a GHZ state, you measure the GHZ state, and you sort of say, oh, this is my gate fidelity, under the assumption that spam is very low. But this is not true, right? If you try to sort of measure the identity, and you measure the identity on the ground state, oh, great, I have a perfect identity because you know, the system decays to the ground state. If I measure the identity on the excited state, well, I will have T1 decay. So I get two very different answers with this methodology on my probing of the identity gate. So the way around this is quantum process tomography. And what we do here is, now instead of doing a single state tomography, well, we do a set of state tomographies. We have a bunch of orthogonal input states, 4 to the n, and we just apply tomography to all of them at the end. So we look what happens to each of these states, how they rotate. In a hand-wavy way, you know, you need 3 input states to figure out on which axis you rotate in the 3-dimensional Bloch sphere space. And because it might not be unitary, you need sort of like another one to see if the kind of contracts all. This is all good and nice. It gives you a lot of information about your quantum operation in terms of like the chi matrix or PMT, but it scales even worse. Now it doesn't only scale 3 to the power n, but it scales 4 times to the power n times 3 to the power n, so like 12 times to the power n. So even doing like 2-state tomography, you need to do, what is it, 244 different measurements. This is very expensive. The reconstruction is now even more expensive because now you have to do MLE not only on one sort of like set of quantum state tomographies, but like an intricate set of like 4 different ones or 4 to the n ones. And there's such a thing as having too much information. Like having these matrices is not always immediately clear how to interpret them. Sometimes you just don't know what to do with it. Maybe there are so many errors and you're like, okay, again, I have all this information, but I can't interpret it. Oops, right. There are, again, multiple variations that I'm not going to go through. Just if you're interested in, some of them try to bring down the overhead with ancilla qubits and multi-qubit measurements, multi-qubit interactions, or again, compressed sensing. It's just like ways and tries to make this more efficient. Now, as I mentioned before, one problem of quantum state tomography and obviously then quantum process tomography is spam. So if you do state tomography, we assume, we don't know rho, but we assume measurement is perfect in state preparation. If you do process tomography, well, we assume our preparing pulses to prepare the initial states are perfect in the measurement as well, but we don't know the process G. In measurement tomography, it's sort of the other way around. We know exactly what state we prepared, but we don't know really the measurement. Now, this is ideal in the textbook, but not in our reality. In reality, these things are often also faulty. We don't know them exactly. And so this is where gate-set tomography comes into play, which is just like a method to really probe all these things self-consistently, like with various experiments at once. And I'm going to be honest with you, to me, gate-set tomography is a black box, and I just don't have the mental capacity to really understand the true details. But, there is actually a software package from Sandia, Pigsty, that anyone can download. It's open source. So if you're a PhD student in the lab or researcher, basically you can just press and go, and it will do everything for you if you're not interested in the very intricate details. Yeah, again, the only thing to worry about is it scales even worse than process tomography, because now you have a gate set, various gates that you have to consistently probe as well. So it's not only 12 to the power n, but again, something depending on your gate set. All right. Any questions so far? Yeah.
You mentioned that in state tomography you restrict to physical states, and you have to enforce this due to shot noise. How do you do it in process tomography? Do you do it on the individual state level? So each state tomography that goes into process tomography?
Probably. I mean, I've never really looked into detail of these things. Personally, I very rarely do gate set tomography, or I've never done gate set tomography because it's too much of a pain, and I've very rarely done process tomography because it's also a pain. The kind of methods that I often stick to are the ones that I'm going to talk now. I mean, it's also a little bit of a philosophy, right? Some people are really liking, Sandia really pushes for gate set tomography, and they're good at it. They know how to interpret these results. They know how to do all the optimizations in terms of reconstruction, that it doesn't take too long. There's also this so-called gauge freedom, because now what you probe is not just the gate, but you probe the relative gates to one of each other. And when you reconstruct the process, you get a sort of matrix, which might not be the one that you expected to have in your lab system. An X gate might then look completely different, and now you have to find the right gate, so there are ways to enforce that as well. The thing that I most often use is randomized benchmarking. So what is that? It's basically a random sequence of Clifford gates that we apply sequentially on our system. And what is a Clifford gate? It's just basically a gate that when you apply it to a Pauli matrix and the inverse to it, you get another Pauli matrix. This makes it very efficient to calculate it. You can now apply these Clifford gates, and in polynomial time, you can calculate the actual outcome of the sequence. We can decompose those into log n to the power 2 log n elements of a single qubit and 2 qubit gates. Most systems only have single and 2 qubit gates. And if you do the counting, the single qubit Clifford group has 24 elements. The 2 qubit Clifford group has 11,512 elements. And the 3 qubit Clifford group has roughly 92 million elements. And you have now to randomly sample from. They sound big, but for a classical computer, these numbers are small. You just pre-generate them. You randomly sample them, stick them together, run your sequence. This is just some technicalities. The Clifford group is a so-called unitary 2 design, well, actually 3 design, but for RB it doesn't matter. 2 design is just like an approximation to a distribution over the Haar measure to the second momentum. Think of it as like variance, like first momentum mean, second momentum variance. And the Haar measure is just like a truly uniform probability distribution over all quantum states or over all quantum operations. Now, the way this works in terms of randomized benchmarking is you apply the sequence, and then you calculate the inverse with a single Clifford, and you undo it. What that means is if you have no errors in your system, the undo operation should bring you back to your initial state, right? Because like if no errors happen, you just undo it, you end up in 0. This has some nice features. First of all, you only need to measure what's the probability to return to the 0 state. And because you want to make sure that it's truly random, you repeat this sequence k times, which we call seeds. And the experiment looks like this. Every dot here is the return probability of one k sequence with m elements. And we go out here, for instance, to 1,000 Clifford groups, 1,000 Clifford gates. And you see some are better, some are worse. It's just the way how this sort of like random picking from the sequence happens to be. And what all you do now is like an exponential fit of your decaying data. And from that, you can calculate the average Clifford error. So all we get from this is the average Clifford error. Now, you can make some assumptions. For instance, what is my decomposition into my true basis gate set that I have available on my device? I can count how many 2-qubit gates, for instance, I have per Clifford, and so I can divide it through that number. For instance, at IBM, the way we decompose it in Hadamard's and S and 2-qubit gates is we have 1.5 2-qubit gates for the 2-qubit Clifford, so we divide this number by 1.5. This gives us sort of a rough estimate on the 2-qubit gate fidelities, or if you do 3-qubit Cliffords, then it's like 2.2. I think we're just going to skip the next slide, because this is just like to show that this is really an exponential decay, but you can look that up yourself later. But I want to carry on with some properties of randomized benchmarking. One reason why we tend to do randomized benchmarking is it's insensitive to spam. Because what we measure is not where it really starts. What we measure is the exponential decay. And so spam, meaning preparation and measurement error, is sort of encoded in the A and B factors, or the offset, right? You can take that and make some calculation to get like an estimate on spam as well, but we rarely do that. The inverse is sufficiently calculatable because it's the Clifford group. And one nice thing about Cliffords is that they do so-called twirling. I guess you heard that already. It basically turns every error channel into like a depolarization error channel. And this makes it a little bit easier to treat it. Theoretically, we can go out now to very long sequences, and so like, to get a nice exponential fit. The bad part of randomized benchmarking is, well, it gives you only it only gives you an average Clifford error. You don't know if you decompose it into your basis gate set. You can have like one gate perfect. Like for us at IBM, we use like Z gates. These are just like frame changes, meaning we just like change, in software where the pulse is in terms of phase. So this basically happens on, with an error of the DAC resolution 10 to the minus 7. But we can't truly tell where the error really comes from because we only have an average error. And it doesn't tell you where the noise comes from, right? Everything turns into a depolarizing channel. So you could have like only coherent errors or only the incoherent, so you can't even tell the difference between those two. And you can't really tell if one, as I mentioned, one of the gates has maybe very low errors and the other gate has very high errors. It just gives you this average. But it's a nice, fast technique that doesn't run long, and so that's why we often use it. One way a little bit around that is so-called interleaved randomized benchmarking, where we take the sequence, we sort of like repeat the sequence, but now we interleave a gate of interest another Clifford gate, and 2-qubit Clifford gate could also be a C naught. That's Clifford gate. And we just like repeat it in between, and we take both curves, and we compare the two decays. If they're fairly separable, you can make a statement how much error is actually introduced by your interleaved gate. Now, what I just want to quickly point out here is the two curves have to be separable. Like if they're too close or on top of each other, don't make any assumptions about your interleaved gate, because now you try to distinguish two things that are basically the same. Like the amount of error you get from every other Clifford group, every other Clifford gate is sort of the same as your interleaved. And again, you can't tell the difference because you look at averages. One thing that we use very often is just like, again, a small modification of the sequence is purity RB. This can tell us how much error comes from coherent and how much comes from incoherent sources. And all we do is like just remove the inverse gate, and we apply sort of like a state tomography sequence at the end and try to figure out what the purity of the system is. We can measure the purity decay, and that sort of gives you an idea of what comes from incoherent versus coherent errors. Now, RB is a huge zoo, and I can just like, if you really want to know a little bit more, there's a newish review paper on the archive describing a lot of these methods with all the references in there. Even more references, some very early papers by Knill and Joe Emerson, describing it in like sort of like different ways, and sort of like a little bit more description by Iswar and Jay, and then just like some selection of papers I'm just mentioning it here. All right. I think we can maybe take a quick break. 5 minutes. Hey.
I have a question. So you define the readout error as initializing the state and measuring it and looking at the difference between what we were supposed to initialize and what we measure.
Yeah.
And after you were speaking about state preparation and measurement error, but then in the readout error, the state preparation.
Yeah, it's all a little bit convoluted, right? Like, if you try to measure this A matrix, you sort of have to make the assumption to some degree that your pulse that brings you to the excited state is much, much better than anything else. Okay. We know that this is true. At least in our systems, we can do like single qubit gates with 4 nines, 5 nines error, but like our readout and state preparation error is in the order of like 0.5% or like 0.1. So these are orders of magnitude different. So that's why we can trust. Okay. If they're similar, well, it gets convoluted.
Okay, thank you.
Yeah.
So I was wondering with the randomized benchmarking,
right.
Like if you're only on, what's it called, using Cliffords to make your circuit and run them, how do you know that your device works on non-Clifford?
So the Clifford is, well, that's a good question. You don't have to.
No.
I think Clifford is very much a historic thing because people realize that it's efficiently calculatable. But we never go beyond like 3 because like Clifford sequences just become infeasible experimentally, as I will show if you go through. And so you can just do like SU2s or SU4s or whatever you like. But to come back to your point, it's a unitary 2 design. Yeah. So the twirling and like reaching every bits and part of the Hilbert space follows the same as if you would sample the Haar distribution.
No, yeah, I mean, like in principle, you could also just like replace some of the S gates with double T's and see like if it does. Like,
yeah, but this is then in terms of like the decomposition.
Oh yeah, no, yeah, exactly.
It's like none of the experimental platforms can implement a Clifford. No. You have it's like we used to have like U1, U2, U3s. Yeah. Now we changed to I think S and Z gates and or S square. I don't remember which one we have now. 1 or 2.
Yeah, I mean like so like I don't know.
Like we can't like the way we run gates, we can't even actually implement the Hadamard. We have to decompose the hard part.
No, that makes sense. Because like I mean, it depends on how you're doing your inference. So like I'm just working with compiling stuff, and that was also my thing. Is like I can make decisions as my how I can like reconstruct my circuit to have a certain set of gates. But if those gates are not natively supported by the hardware, then I might as well go directly to what is supported by the hardware, because I might make better decisions that way.
It depends what you want to probe. As I will show now with the holistic benchmarks, one reason why we, in quantum volume, go for SU force that no one can implement, this is just an arbitrary 2-qubit gate, is to force the transpiler to be also optimized.
Yeah.
So now you get this random gate, and you need to know how to transpile
To be
that.
able to do those things. No,
And this is just like the level you want to probe your system, right? If you
Yeah.
don't care about the transpiler, well, then make it as optimal as you know how to do it, and don't leave it to the benchmark. But if you create a benchmark that should test that too, well, then make it as hard as possible.
Really good at that. No, yeah, exactly.
There's a paper recently, maybe you've seen it. I didn't see it there, so but the direct randomized benchmarking, also by the Sandia people.
They, I think, they didn't retract it, but I think that has exactly the problem of like, the problem of not being easily calculatable, because they move away from Clifford's. I think they do like random SU2s in between. At least what they do is like they have like a whole circuit, and then they do calculate the inverse of the circuit. But this is like matrix inversion for like an n by n matrix. That's why we do quantum.
No, yeah, exactly.
This gets even harder than just like.
I mean, it works for now because we don't have very large matrices.
Yeah, but like go to already 10, it's just like very costly.
No, exactly.
What they have now is mirrored. All right. So before we carry on, are you following my dog?
Yes.
Okay. No, I'm kidding. All right, let's start with holistic benchmarks. Or not yet. Yes.
Try now? Okay.
Cool. All right. All right. So, holistic benchmarks. Well, this is at the top of the pyramid, consisting of like various approaches. And holistic or holistic means it's just like you try to probe everything, like the whole of what it is. To me, personally, there's a little bit of semantics going on. Some people call certain things holistic, where I maybe more as a purist would say this is not holistic. But just because, like, to me, a holistic benchmark should include everything. From your device to your software to whatever you do in additional pulses, optimal control, yada, yada. Now, you might wonder, why do we even care about holistic benchmarks? You know, we can probe all of these bits and pieces of a quantum computer individually. We can probe how good qubit initialization is. It should be very low. 1 and 2 qubit errors, we can estimate them with, you know, GST if it need be, or with randomized benchmarking. Should be low. We can measure coherences, easy, quickly done. We can quantify measurement. We can even quantify, you know, software by itself, like, you know, what is the connectivity, how do we map circuits to device specifications, and so on. And so why do we even need that? Well, to be sort of a little bit, you know, repetitive, probably for everyone, is, you know, quantum coherence. The whole is greater than the sum of its parts. And in sort of like very naive terms, it just means, you know, now you put things together and they might work in a very, very different way than when you probe them individually. Think of, you know, you probe 2 qubit gates, you get very good gates, and now you add a spectator qubit. Well, in some systems, you just get a little bit of leakage, so your 2 qubit gates get worse, or you have a big chip, let's say a superconducting chip, and you apply a microwave tone here, and you have some box modes that carry over that you never were aware of, and suddenly excite a qubit on the other side of the chip. That's something you won't be able to see on a small level system size. There are, again, sort of like 2 main approaches, I would say. One follows more like random circuits. Again, this is more of like you try to measure an average circuit fidelity, an average circuit error. And it's more of a general statement in terms of like how well can a quantum computer implement a arbitrary circuit, like some circuit that you don't know what will be running in the near or spam in the far distant future. If need be, you can make these benchmarks spam independent. Again, it's very similarly to randomized benchmarking, but it makes it a little bit less holistic because now you don't probe measurement as well at once, right? Sort of the negative thing of this random circuit approach is there's not a real life use case. None of our algorithms is truly random. They have certain structures, meaning that, you know, there will be sensitive to a very different array of errors than randomized circuits, because the randomized circuits, they twirl. And so they turn every coherent error, most likely, into a depolarizing noise channel. And again, coherent errors are bad. The other approach is, well, apply an algorithm, an application, and measure its outcome. Best case would be, you know, some algorithm that we believe that we want to use in the far distant future. But this is exactly the problem. We don't know what a quantum computer will be capable of. So we have now the difficult decision to make, which algorithm do we want to run? You know, a VQE algorithm is sort of inherently insensitive to coherent errors, because like, if you slightly over-rotate, well, you have your parameters to adjust, and you know, you will sort of like spiral down to the right one. If you apply a GHZ state preparation circuit, well, this is one of the hardest things you can ever do, because like, it just like needs one error on one of the qubits and your whole GHZ state is gone. So what do you pick? How do you quantify that? And so, when you try to make improvements, this is the whole goal. As an experimentalist or even theorist, we try to improve things. We try to tweak knobs, see if it's better. But if you do this sort of application-based approach, what could happen is you improve it for this class of circuits, but it doesn't work on the other class. But we want to have a general improvement, right? The other problem, in general, with holistic benchmarks is how do we measure it? And once we measure it, the outcome, how do we verify it? One approach is, again, similar to RB, is apply an inversion. Just bring the system back to its initial state. This has advantages, has disadvantages. Advantages is you just need to measure the return probability, so that's easy to probe and verify. The tricky part is how to calculate that inversion, how to do that inversion. And, could be positive or not positive, depending on how you see it. It can be insensitive to spam. But it's most likely, if you're not careful enough, can be also insensitive to coherent errors. The other approach is, well, do sampling of a distribution. What we measure in a quantum computer, if you have many, many circuits, it's just like an outcome 0, 1, 1, 1, 0, 2 to the power n bit strings. How do you sample that, right? There are a lot of bit strings, and now you have to reproduce the ideal distribution. A, you have the sampling problem, and B, how do you compare your experimental distribution to something that should have been? So this kind of requires you to the outcome. But again, this is the whole business of quantum computation, right? We try to do something that is not classically tractable. So how do we scale that up, right? Probably the best thing, once we're far ahead, is pick a problem that is out of for interest, that is hard to solve, but easy to verify, right? I think this is something that we're not there yet, because these circuits tend to be pretty large, and they will just spit out garbage. All right. Let's start with multi-qubit Clifford randomized benchmarking. Initially, Clifford randomized benchmarking was sort of invented because of the the theorem that Cliffords are easy to calculate or efficiently calculatable. That's all good, fair, but in an experiment, it turns out this gets quickly really hard. So what you see here is the true decomposition of an example Clifford on a hardware available gate set. One Clifford, qubit Clifford, you need sometimes two qubit gates. The 2 qubit Clifford in this example needs two qubit gates. The 3 qubit Clifford needs already 4 in this example, and here's the assumption even I have an all-to-all connectivity, which not all systems have. If you go to 10 qubits, oh, this circuit becomes already huge. This is 1 Clifford gate, right? Now you can do back on the envelope calculation. You assume you have 3 9 2 qubit gates. This is world-class gates at this point in time. You try to apply 1 10 qubit Clifford gate on an all-to-all connectivity, and your fidelity drops down to 0.9 for 1 Clifford. Now you have to apply multiple Cliffords and the inverse, and then you have to fit an exponential decay. Well, good luck doing that with a couple of points, right? If you want to resolve very high fidelities. So experimentally, this gets very quickly infeasible, and that's why we don't do it. The highest standard Clifford RB that has ever been done, actually just a couple of years ago with my colleague David Mackay, was just on 3 qubits. No one's going beyond that. How do we solve that problem? Well, there are a bunch of ways. I'm just going to mention a few of them. One is cycle benchmarking. Basically, you randomize the input. You have a gate G that you want to infer. You apply random polys, so sort of twirl it. You can repeat that cycle here, and from that you can get pretty good spam-free estimation. So this is a technique fairly recently developed by Joe Emerson and my former colleagues in Innsbruck. I would sort of call this more a characterization technique rather than a verification, because you try to infer how good your gate here is or whatever that operation is. Another way that people at Sandia have come up is so-called mirrored circuits. Basically, you randomize your input. You apply some circuit unitary. The circuit unitary can be various things. It can be, something that looks like an algorithm. It can be truly unstructured, random circuits in the way of like quantum volume, for instance. Or it can be something like a repetitive error amplification sequence if you want to amplify some errors. Now, the important part here is, you try to undo that initial circuit evolution, but not with an inverse gate, but just like sort of like turning every gate with its inverse. You go forward in evolution, and then you go backward in evolution. If you do that without this middle layer, you have the problem that you might undo coherent errors again, right? Assume everything is perfect, but you have slightly over rotations. Now you evolve, and then you evolve back, right? It's kind of an echo. So what you have to do is apply a layer of like randomized polys to sort of twirl these errors. There, currently, the discussion is, because this is also a fairly new technique, is this enough twirling? Like, does it really turn like coherent errors and stuff like that into a depolarizing channel? Okay. Now, the next part, a couple of minutes, I'm obviously biased with that. This has been 4 years of my life. I want to introduce to you quantum volume and hopefully show you why I personally like it, but also like things that are maybe not that great. So quantum volume is this single number metric that tries to assess the performance of a quantum computer. We've come up with this a couple of years ago, and basically what quantum volume really tries to do is to probe each and every bit of your quantum processor. The number of qubits matters, so the more qubits you have, the higher your quantum volume could be. Gate and readout errors matter. The lower they are, the more like depth in circuit you can go. The connectivity matters. This is something where we, on purpose, almost shoot ourselves into the foot, as I will show later. The kind of gate sets you have, right? The more different gates you have, the higher, variability you have in your transpiler to, decompose arbitrary gates. You might make it faster, you might make it better. So in that sense, quantum volume also probes your software stack. How good is your transpiler? And I won't go here into detail, but to us, transpilation has made a lot of like improvements in terms of like getting to higher quantum volume numbers. And personally, to me, this is sort of like where I'm, the hill I'm personally going to die on is any kind of benchmark we have for quantum computers needs to be made in such a way that it's hard to cheat, maliciously or, not on purpose. And so quantum volume sort of asks the question, can a circuit, an arbitrary circuit, be run by ignoring, like totally ignoring like times, repetition rates? It's just like the quality of it. And what quantum volume is basically the largest random square circuit that can be successfully run on a quantum computer. And as you can see, I highlighted some of these words, and I just want to go by them like word by word. So what does it mean to have like a random circuit? Let's take as an example 4-qubit register and apply a random SU4. An SU4 is just like, a 4x4 matrix, unitary matrix, that describes a arbitrary quantum operation, or quantum operation. Now, we just randomly picked these 2 qubits, and in this register we have 2 more qubits left. We just apply a second random unitary. We call this a layer, and now we repeat the same process by picking different random qubits and different SU4s, and we just repeat it over and over again until the number of layers is the width number of qubits, and that's why we call it the square circuit. Now, what does it mean to measure it successfully? Well, we measure the outcome of this circuit. We measure the so-called heavy output probability. If everything is perfectly fine, no errors, we get a probability of 85% roughly. If the whole thing is totally depolarized and we just like get garbage out of it, the probability is 0.5. You just got random bit strings. And we set the threshold at 2/3. So if you're above the 2/3 line, you succeeded in the test. If not, you're below the test. And now the way it works is You know, maybe you start out with 3 qubits and these 3 layers. If you pass the test, you carry on. You take 4 qubits, 4 layers, you pass the test, you carry on until you fail. Now, what is this heavy output probability? The whole circuit can just be, you know, rewritten as a big circuit unitary. And we apply the circuit unitary into a classical computer and compute the ideal outcome, the state vector. From the state vector, you know, you get this probability distribution, which just tells you, you know, it's the amplitude squared for each of the bit strings. It just tells you, you know, the bit string of 0, 0, 0 should be observed with about 8%, 1, 1, 1, with whatever, 2.5%. Now, all we do is we just sort these outcomes, the ideal outcomes, from lowest to highest probability. We set the median value. And now everything that falls into the, from your side, the right side, at high probabilities, we call that the heavy output. So every bit string that belongs to this set is called heavy. Kind of makes sense, right? Now, this is all classically. This is sort of the part that does not scale for quantum volume, because we have to pre-calculate for every circuit that we run, for every size, we have to pre-calculate the ideal outcome. We apply the thing to quantum computer, you know, apply the circuit unitary, and I here on purpose just put a circuit unitary, because now this is the part where the transpiler jumps in. The way you want to apply the circuit unitary is totally up to you. If you have some magic wand to apply it and get perfect outcomes, hey, great. If you don't, well, you know, that's what we try to test. So you apply it to your quantum computer, and you get a bit string 0010, and you know, this was part of the heavy output probability. If you get 011, it wasn't part of the heavy output probability, and I'm very proud of my animation here. You just measure it a bunch of times. Every time your bit string is part of the heavy output probability, you make a mark in the, you know, success bin. Every time it doesn't, you make a mark in the fail bin. You count fails over total, or successes over total shots, and you get a heavy output probability in this particular case of like 0.97. So this particular circuit passed the test, but this is only one single random circuit. So the way we do it is like pick this random circuit, prepare it in a kind of like
I don't see how the 2 sigma happens. Like if you see the data points, it really looks like a...
Oh, so what you look at is the average, the red curve is above 2/3. So, you know, some circuits are really hard because they need a lot of swaps or they just don't work as well. Some circuits are very easy, so this is the spread of circuits.
No, yeah, but I think the spread is somehow uniform, right? Like you do this 2 sigma gray curve, but if you look at the data, it looks uniform across the number of trials. So I don't see like how...
Not sure I understand what you mean. Yeah, it's the sigma.
If you see the blue points, it really looks like a uniform blob.
Yeah, dense. You have more and more data
Okay.
near the red curve.
One thing to sort of like what you might realize, the data here is a little bit sort of digitalized. This is due to the number of shots. So if you look, other people have run way fewer shots, like 20 shots, and the digitalization will just be bigger. Just like this is your resolution of the heavy output probability, right? In principle, you only have to run once. And what you would get is like either 0 or 1. So this is like the bare minimum. If you run it 1,000 times, well, then your resolution just like becomes bigger for like the individual heavy output probability.
Just to make sure that I understood it correctly, it's only random 2-qubit unitaries that you apply.
Yeah, it's random 2-qubit unitaries on random pairs. But this is...
And then the ideal probability, you said it's approximately 0.85?
Yeah.
But like above 0.85 or like...
No, below. So some circuits can go slightly above. This is just like, I might talk about it later a little bit. A random circuit follows the distribution to Porter-Thomas. Sort of like transform QV into a logical QV. At some point when we have logical qubits and we want to do a algorithm on logical qubits, you still have to do mapping, you still have to do, you know, benchmarking, so you can maybe come up with like QV 2.0. The bad thing on the other side is it's a single qubit metric. Like when people come to me and ask me, oh, your device has QV 512, can I run this? And then I got to say, well, I don't really know. It's more of a metric to pass a test, to guide us. Initially, it was also actually for us internally to see, are we making the right progress? Can we make our software, our devices better, and like just run bigger and bigger circuits? But it doesn't really tell you what you actually can run. And if it fails, you just know that you failed. You don't know what failed. So you could have perfect gates, but your readout is bad. You don't know that a priori. So you have to do all these different tests to try to figure out what went wrong. So the whole benchmark pyramid to me is like important. It's not just that we can run this. A sort of extension to that is by Sandia, is so-called volumetric benchmarkings. Do sort of the same, but don't limit yourself to square circuits. Do rectangular circuits. This is great. It's just like way more work for us. I don't really want to measure like the whole plot here, because like the quantum volume measurement takes already half an hour, and if I have to take here every dot, I'm going to be measuring forever. But you know, this is one way to really extend the amount of information that a quantum computer maybe could run, because like now you can ask the question really, hey, does my circuit run on this machine? Yeah, you get an estimate. You know, you have 8 qubits and you know, maybe depth 8, 9 or whatever, and you say, oh, it's maybe on the edge, but probably should work. If I go beyond that, it might not, and so forth. You don't even have to limit yourself to QV-style circuits here, like according to Sandia, you can run any kind of circuit if you like. It just changes sort of like your benchmark then, but that's the way it is.
Sorry, was that experimental data or something like that?
No, this is a simulation. I just took it from the paper. No, it's a simulation. All right. Yeah, I sort of like mentioned that, right? One of the problems is when you have big circuits or many, many qubits is how to sample it, right? You have 2 to the power n bit outcomes, so basically you have to measure this huge distribution, and we just can't measure forever. Like, we can sample only some amount of time. And so really, the question is, how can we replicate, even in the ideal case when we don't have any errors, the distribution, you know, if you want to make some comparisons. And there are sort of a couple of like approaches I want to quickly mention. One already mentioned is like the heavy output generation. Basically just create 2 bins. Is it heavy? It falls into the heavy bin. Is it light? It falls into the light bin. There's bin output generation. Basically you create n or m bins that are larger than 2, but smaller than all the bins available. Or you do something like cross entropy or Hallinger fidelity or whatever, where you basically have to resolve every little bin. I think I'm going to skip these. This is just like how cross entropy is defined. It was used by the Google people to do their supremacy paper. It's just, again, one metric to measure the distance between 2 distributions that you can only sparsely sample. You can define the fidelity with the cross entropy when you compare it to like the uniform distribution. Yeah, the next couple of slides are basically something that we've been doing for a while ago. These are just like different kinds of circuits. The diagonal entries, so you should get like a delta peak in the distribution, but obviously in an experiment, it's as hard to get a fully, completely mixed state as it is to get a perfectly pure state. And this is just like, depending on how you bin it according to the ideal distribution, or you bin it according to the experimental distribution, you can actually use it to distinguish coherent versus incoherent errors. The last couple of minutes, I want to sort of spend a little bit on application-based benchmarking. And so, as I mentioned, you know, random circuits, they're great because they're sort of like a generalization of circuits that we can run, right? But they don't have a real, you know, use case, and they sort of like turn everything into depolarizing error channels, which means coherent errors that can be really bad for applications, we sort of like, you know, put them under the rug. And so, we should maybe try to run some applications have structure. And there are like various approaches to that. I just want to mention a few of them. There's this cousin bench. This is just a huge Git repo of, I don't know, more than like 60 different circuits that are defined on the QSM level. QSM is this like machine language-based level developed by IBM and others, divided into low-scale circuits, mid-scale circuits, and large-scale circuits. They have various characterizations. We characterize them by width, depth, density, retention lifespan, which is something like related to coherence, how much measurements you do. Entanglement variance is something like where you apply 2-qubit gates across distances. And here what they would sort of like measure is this fidelity, which basically requires you, A, to pre-calculate your ideal outcome and also to sample your entire distribution. So this is a little bit tricky. And so maybe a year later or so, Supermark came out, I think, from Princeton. This is a collection of 8 circuits. Whatever they have, like GHZ state preparation circuits, Mermin Bell, phase code, bit code, a few others like QoA, VQE. They span these circuits over a vector space or feature space. And program communication means, I think, how many 2-qubit gates are like spanned over like far distant qubits. Circuit depth, okay, that's self-explanatory. Entanglement ratio is how many 2-qubit gates versus single-qubit gates. Parallelism, how many 2-qubit gates run in parallel. Liveliness has, again, something to do with coherence time versus sort of circuit execution time, and measurement. And so what they basically define as a metric is just like for every single circuit, you have a different kind of metric. It's then just like a little bit harder to compare different devices because now you have these big collections of circuits. Each circuit has a different metric, and so it's just a little bit more complex. One last one that I just want to mention is QEDC benchmark suite. It's developed by the Quantum Economic Development Consortium. This is just like a consortium of a bunch of companies in the US, the NIST, and a few others. They have like 11, 12 different circuits in 3 different categories, like tutorial, like Bernstein, Vazirani, some subroutines like phase and amplitude estimation, and some like functional ones like VQE or like Hamiltonian simulation. What they measure is this polarization fidelity. You compare the ideal and the measured probability distributions, and you sort of like normalize it over the uniform distribution. Again, you plot it on this sort of like volumetric background. It's just a different way. And to me, kind of the big question is like, why these circuits? Why not those circuits? I think these are questions that we as a community need to figure out. There are way, way more. I just like list those. You can look up the references. And so let me sort of like go a little bit beyond the current benchmarkings. Is so far we just had like this device benchmarking that is more application driven and NISQ driven. But I think we have to expand the benchmarking pyramid to include now things that will be important to fault tolerance. That means now we should also start like benchmarking mid-circuit measurements and resets. This is something barely people have looked at in terms of benchmarking. How to do like syndrome repetition and ancilla measurements. And then on top of that, even like we need benchmarks to probe which code is better and so forth. All right. The last couple of slides, I just want to spend on even beyond quality benchmarks. So what we looked at mostly here is like, we think we have to scale to more qubits, and we think we have to scale towards higher quality. And quality we benchmark with this pyramid. Qubits, we just count them. And we know we can trade these things. If you often go to larger qubit systems, your quality goes down. But sometimes you can add ancilla qubits and maybe improve your quality. So there's a little bit of a trade space. And maybe a couple of years ago, we sort of realized at IBM that there's actually a third dimension to it, and it's speed. Because now we expand the trade space, especially if you do like error mitigation things. Maybe you can run more things, but get better results. So speed matters. Like, you know, if you, in the far future, we have a working quantum computer, and let's say you have two vendors. One requires you to wait a month to get the perfect result, and one requires you, or just like takes half a day to get a result that is 90% of the time true. What will you do? Let's say the faster one and the slower one cost the same. If you're a university, maybe a grad student, you might be willing to wait because like you don't have so much funding. If you are a business, oh, you're going to take the faster one because you're just going to run it twice or 3 times to pay the money because like for you, time matters. So, you know, speed is kind of a metric that we should start to probe as well. And so last year, we came up with a metric that we call CLOPS, an unfortunate name that I didn't vote for it. It's circuit layer operations per second. And it's basically just kind of a quantum volume, but how fast can you run quantum volume? You know, we imagine that people will send circuits to a server. The server will handle everything, and then just like spit out the result. Right now, before like what we call runtime, if you ran like VQE, you send something to the cloud does some, or the quantum computer does something, sends you back the result, you optimize and get a new set of parameters, you send it back. So it's this huge circle, and we want to move that into the cloud, that basically you just send one program, the program gets executed far away from you, does all what needs to be done that you defined in your program, and you get the result back. And this is why we sort of like try to mimic that, how fast it can go. And the idea is basically, you know, take a set of quantum volume circuits, 100 circuits that you already ran to measure your quantum volume, parameterize them, like the SU force. Do not take the random SU force, but like parameterize them. And you know, now you take the first circuit, you measure it 100 times, 100 shots, and then out of this outcome, you feed the outcome into a random number generator, and the random number generator creates a new set of parameters for the sort of like same structured circuit. And so this is basically the loop we try to run. Have these 100 circuits, parameterize them, run it 100 times, feed the outcome of it into a random number generator. That creates a new set of parameters for the circuit, run that 10 times, and then the new circuit drops in. And so CLOPS, or circuit layer operations, is basically defined just as the number of these layers in a quantum volume times 100,000. 100,000 just comes from, you know, 100 circuits times 100 shots times 10 iterations. And this just like tells you how fast can you run such a program. All right. So, in summary, we've looked at how to, you know, characterize a quantum device on a device level. We've looked at, you know, how to characterize quantum operations and why we have all these different techniques to do so. There's this whole zoo of benchmarking that you can pick from to answer various questions. And to me personally, you know, as an experimentalist, I think this is one of the most important and underrated toolboxes, you know, in our community that not too many people work on. And I would wish that, you know, a lot of more community effort is there to like figure out how to do these things because it's very important. Last but not least, you know, I want to take the opportunity. We always have looking for new talents. I don't know if there are job openings out there right now, but like visit us on our LinkedIn page. With that, I'd like to thank you, and if there are any questions, I'm around.